All right, let's get this started. So this is going to actually keep building on the ideas we just did, so it'll be easy transition. Okay, so um, right. So we talked a little bit about converging to a stationary distribution, and we're going to actually also connect that now to more structural properties of the graph. So right now we have an analysis in terms of the eigenvalues of a graph, right? But when you look at a graph, you don't see eigenvalues. You see edges, you see cuts, you know. So we're going to kind of come up with an even more maybe interpretable and combinatorial bound. So, okay, we've already recapped once. We can't recap twice. So we just did this, right? And so this time, I'll introduce something called conductance and trying to get a low conductance cut. It's going to be similar but slightly different than sparsus cut. Okay, and we'll get a mixing time that's based on the conductance of a graph, which for the moment, if you think of it as sparsus cut, is sort of like saying based on the strength of the sparsus cut can bound your mixing time. And then we'll do an algorithm for finding low conductance cuts. So let me just define what these things are and get it going. Of course, we won't do all of it today. So remember, this is sparsity. So in the sparsus cut problem, you had some like demands and you cut some edges and you want to cut few edges but split up many demands. That was the problem. I think you've like solved this problem twice already, so you know it well. An important case is the uniform case where every vertex has weight 1, okay, because this is often used in divide and conquer. So conductance, well, it's coming up. All right, so some notation. I guess you guys already know all this notation, except for maybe this one. The volume of a set is just going to sum up the degrees. Okay, so when I refer to volume, that's going to be the sum of degrees over a vertex set. And the conductance of a particular set, instead of dividing by the number of vertices on one side, we're going to divide by the volume, the smaller of the two volumes between S and the other side. Sum of degrees. And the conductance of a graph will be the minimum conductance over all possible sets. Okay. So that is, I think I have some nice examples for us. Okay, so to help us appreciate the slight difference between two definitions, so sparsity will be just divided by number of vertices, and conductance will be divided by the volume, sum of degrees on each side. Okay, and so here are three different kinds of graph: two clicks connected by a couple edges, one click and one cycle connected by a couple edges, and just one click. Okay, and you have three choices. Well, you have four choices, but the three main choices are high, medium, or low. Slightly ambiguous, but hopefully, you know, you'll figure it out. Or you can choose not to vote, of course. Okay. So, so first of all, who is not voting? Okay, one person is not voting. There's a lot of responsibility on the n-1 of you. Okay, let's take this. Will this have high, medium, or low sparsity? Okay, who votes high? Who votes medium? And who votes low? Okay. Okay. We'll do all the sparsity rows first. Okay, let's take the next graph. Will this have, who thinks this will have high sparsity? 2. Okay. And who thinks this will have medium sparsity? 5. Okay, who thinks they'll have low sparsity? Okay, didn't add up, but that's okay. So it's like 3 high, 4, I think it was like 5 medium, maybe 10-ish low. Okay, 4 highs. Okay, and now let's look at a click. Will this have high sparsity, medium sparsity, or low sparsity? Who has high? 2 for high. And then what about medium? And then what about low? Okay. Okay, let me clarify one thing. So high sparsity just means higher ratio minimized over all S. So no matter how you try to cut this, you're going to cut a lot of edges compared to the number of vertices on each side. So this is probably the highest sparsity. Uh, so at least two of you went the wrong direction. Um, and now these two graphs, the sparsest cut is probably just the middle two edges. Yeah, so okay, so you could just isolate like one of these vertices, um, but you're going to still have, so you want a lot of vertices on each side to decrease the sparsity. So you're worried about what's the sparsest cut in the graph, the minimum sparsity. So you want to cut few edges, but sort of have an equal number of vertices on each side. So you probably rather cut the two middle edges than two edges in the cycle, because that'll put closer to even number of vertices on each side. Yeah, so if S is small, the ratio goes up. You want the ratio to go down. So sparsity is the minimum sparsity over all S in the graph. Yeah, so this should actually have the same sparsity probably, whether you felt that was medium or low. So at least three of you were inconsistent probably. Okay. Right, okay, good. So we're getting some sense. Yeah, so sparsity is not really going to distinguish these two as much. Okay. Um, okay. Now conductance is uh, uh, weighted by degrees, right? Okay. So high, medium, low. Who thinks this will have high conductance? The first sum of degrees. It's in the notes. I printed out 50 copies. Okay. Who thinks it'll have medium? Or did you? Who thinks it'll have high conductance? Yeah. No, high conductance means the ratio is always high. Low conductance means there's some cut where the ratio is low. So the conductance of a graph is the minimum over all S. Same with sparsity. So what we're actually going to identify is sort of bottlenecks. So in general, a random walk is going to be kind of have a tough time getting over some of these cuts because it's very hard to escape, right? So, okay, so conductance, high, all right, one half a vote. Medium, low, okay. And the one person who said they're not voting has like been very good about it. So, okay. All right, what about this graph? Who thinks, now we're looking at the conductance. Should this be, anyone thinks this will have high conductance? One for high. What about medium? Mostly medium. Any low? Okay. So the conductance will be better. So conductance is going to oh wait, did I get that? No, this is what people said. Oh no, one person said high. So uh yeah, conductance is going to at least distinguish these two graphs. And yeah, it's hard to say. So if this was actually more exaggerated, and there's really like n vertices over here as n gets really big, then this is actually going to be not so different than this graph because this doesn't contribute much degrees either way. What you really be concerned with is how you're splitting up the clique. Yeah. So if you split in the middle, you can have a lot of volume here and a lot of volume here. Well, volume's in the denominator. So the bigger the volume, the lower. Yeah. Yeah, so sparsity is like for both of these, it's the what's the minimizing s ratio minimizing s. So yeah, high sparsity is probably what you think of as not very sparse, and low sparsity is probably what you think of as very sparse. Yeah, so high value of sparsity, I guess. Okay, and in this graph, who thinks it should have high conductance, and then who thinks it'll be medium conductance? Okay, this you all lost their mind. Low conductance. Okay. All right. So yeah, so this will also be a pretty high conductance graph. No matter how you separate it, you're gonna have to cut a lot of edges. Okay. Although the value will probably be a little lower than here. Um. Okay. Right. So all right. Let me explain then where this is going, and then we'll do some real analysis next time. Okay. So for whatever reason, I've reintroduced the Laplacian again. This is like the third straight lecture where I've defined a Laplacian. Um, we'll do this next time, but the Laplacian can also be written as the diagonal degree matrix minus the adjacency matrix. You can just verify that with one edge and then sum them up. It's not too exciting. Maybe we'll skip it next time. Um, okay, I'll just do this. So, okay, so the conductance of a set S is the weight of a cut S, which can be written like this, right? So, uh, right. Oh, okay. So we'll prove this maybe in more detail next time. But what's the moral of this story? Okay. So let me define the normalized Laplacian as dividing out the degrees on both sides. Thought I had something here. Okay. Now you have something like XLX is equal to y and y for any y's. Okay. And yeah, I hope I'm not going too fast. But we can do it again next time. Now, remember all this stuff from before, okay? Now, and this theorem from before. Now, you can take your normalized matrix like this, okay? Normalized Laplacian, and we can plug in I minus the adjacency, or D minus A, sorry, okay? And the D's are going to cancel each other out, okay? And you're going to get I minus Q, okay? So what does that tell you about the eigenvalues of M? It's 1 minus the eigenvalues of Q. The smallest one will be 0, and it's going to go all the way up to at most 2. Okay. And, right, this kind of thing. So, good. So, M is going to have the same eigenvalues as I minus R, and, okay, so this is just mapping them back and forth. Lambda goes to 1 minus lambda. Now, and we did, so that's 0. Okay, so what we're going to prove next time, right? So that already tells you there's some connection between the mixing time and some eigenvalues of M, which are related to eigenvalues of L. We're going to show first that lambda 2, the second eigenvalue, second smallest eigenvalue of m, is very closely related to the sparsest cut, lowest conductance cut of the graph. Right? So now the eigenvalue is telling you something about the cuts in the graph. Okay? And we'll prove that, but also, the reason why this is interesting, if I start trying to combine these ideas together, we know that the graph mixes at some rate depending on the eigengap, the gap between eigenvalues. I know the eigenvalues for R or Q start mapping to eigenvalues for M. And I know that the eigenvalues for M are strongly related to the conductance of the graph. And you start working that backwards and you're like, oh, is there a connection between the conductance of a graph and the eigenvalues and the rate at which a random walk will mix? Okay. So that's what we'll prove next time. We will show that the stationary distribution will converge at a rate exponential in the conductance squared, apparently, divided by 4. Okay? So if a graph has really low conductance, which is basically looks like two dumbbells and maybe an edge attached in the middle, it'll take a long time to converge to the stationary distribution. But if it doesn't look like that, if it's like a click, then you'll converge to stationary distribution right away, right? So a graph with very high conductance is going to have a high value in the exponent, and it's going to converge to a stationary distribution really fast. That's what we'll prove next time. But this is a very nice statement because we've sort of taken the math out of it. That was just a middleman, right? Because otherwise you have two combinatorial statements. If the graph is really well connected in the sense of conductivity, I don't have these low conductance cuts, then any random walk will converge very fast to the stationary distribution. That makes a lot of sense. That makes total intuitive sense. If the graph is well connected, you should converge faster to a stationary distribution. This is how we get the quantities correct. This is the right way it turns out to model it. Okay, so that will be the focus next time. All right, thanks. All right. Okay, let's get started. What are we talking about? We are talking about conductance and its relation to mixing time. So conductance is like sparsity, except it's weighted by degree, and that's the only difference. So there's our definition of conductance. So, you're looking at sets where the volume of the set is almost half of the total volume, and you're just minimizing. I mean, look at the ratio of the edges being cut divided by the total degree on the smaller side. Okay. So similar to sparsity, there's some distinctions. We kind of walk through some examples to get some feel for it. Okay. If it's a regular graph, everyone has the same degree, then they're going to be the same up to some fixed ratio. Okay, so right. So today's about relating the conductance to the Laplacian of a graph, and then also relating the conductance to random walks and stuff via the Laplacian. So I mentioned last time the Laplacian can be written as the degree minus the adjacency matrix. Okay, the weighted degrees. You can check this just for a single edge. E is equal to UV. In that case, the Laplacian of this edge was something like the outer product of 1 at U minus 1 at V as a vector. Outer product 1 at U minus 1 at V, right? So if you look at that outer product along the diagonals for U and V, you're going to have a 1 there. And then on the off diagonal U, V, and VU entries, you're going to have -1 because you're going to have 1 times -1. Okay? And Laplacian is just a weighted sum of these terms, so you get that. Okay, so good. And then I introduced a normalized Laplacian, where I'm going to apply d to the -1/2 on each side. Okay, be better motivated in a moment. Or let me connect it to our normalized random walk from before. So this is what we did, I guess, 2 classes ago or last class. This is what we proved. So Right. So, so one way to connect this is the normalized Laplacian can be written as I minus the normalized random walk, okay? And which is similar to I minus the random walk, which means all the eigenvalues of normal Laplacian we already know. Okay, so every time I have an eigenvalue of m, uh, then that eigenvalue minus 1 is the eigenvalue for r just by flipping around what I minus r is equal to m, or I minus q, sorry, means. So q has the same eigenvalues as r, and m is the same as I minus q. So m has the same eigenvalues as I minus r. Good. So, good, we're just making progress. Okay, so the reason I'm really interested in the normalized Laplacian, where I applied d to the minus 1/2, is because of this claim. So the smallest eigenvalue is always 1, is always 0, sorry, because the random walk, the biggest eigenvalue is 1, and 1 minus 1 gets you 0. So that gets you the smallest eigenvalue. So the claim is that if you look at the second smallest eigenvalue, okay, and you look at the conductance of a graph. So conductance of a graph is sort of a natural combinatorial thing. Someone who's interested only in graphs would be interested in the conductance. And it's saying that it's actually bounded by the second eigenvalue of the graph. Okay, so lambda 2 over 2 is always less than equal to the conductance, which is less than equal to square root of the second eigenvalue. There's a 2 in there. Okay, yeah. No, so that comes from, is it still up here? Yeah. So m has the same eigenvalues as I minus r. All of r's eigenvalues are between 1 and negative 1. So it actually can't go negative. So for example, this tells you, okay, so for example, if the graph is disconnected, it's just two separate components, what does this theorem tell you about lambda 2? It must be 0, right? Uh, uh, and that means r has a second eigenvalue of 1, which makes total sense because you basically have two different graphs, then the two different stationary distributions give you two eigenvectors of 1. And our Frobenius theorem said, oh, if the graph is connected, there's only one eigenvalue of 1. It's an if and only if. So things are starting to make sense going back and forth. Okay. Good. Now, the square root lambda 2 is obviously a bit unusual. So, and this limits the usefulness of this bound. Okay, because we often want multiplicative approximations. If lambda 2 is really small, this is not a very good bound. Lambda 2 is not a very good bound because square root lambda is way bigger than lambda 2. Okay, but in cases where lambda 2 is a constant, which means the conductance is very large, then you'll actually get a constant factor approximation. So if lambda 2 is just above any constant, then the difference between lambda 2 and square root lambda 2 is not as bad. And so you have some bound on the conductance of the graph. Okay. So only in some regimes this bound is super useful. When lambda 2 is very small and close to 0, it becomes of less use. And this actually creates certain issues. For example, there's something called the small set expansion hypothesis, which is really basically dealing with how do you deal with the square root lambda 2. If anybody happens to have heard of this or is working in this area. Okay. Good. So before proving Cheeger's inequality, I wanted to point out an important application. So we have some bounds on the mixing time of a random walk based on the eigenvalues, And we now know how to map the eigenvalues of R to the eigenvalues of normalized Laplacian. And we know how to relate the second smallest eigenvalue of M, which should correspond to the second largest eigenvalue of R, to the conductance of a graph. So we put all these together, we can start trying to relate the conductance of the graph um, with the mixing time. So, yeah. So let me address that by first doing this lemma. So if gamma is set by mu2, so mu2 is the second biggest eigenvalue of R, so gamma is equal to 1 minus mu2, then the claim is that the stationary distribution converges at a rate exponential in the conductance squared. Okay, so how do we do this? So I think we should just start with what we proved. So gamma is equal to 1 minus gamma is equal to mu2. Is that right? Yeah. Mu2 to the k square root of this stuff. Right? Yeah. Oh, r to the t, but let me switch that to k. Or I can switch it to t. Okay. Yeah, so this was meant to be a letter and not a biblical reference. Okay. Yeah, so after t steps. Huh? Sorry, yes. The mu's are referring to the eigenvalues of R. Lambdas are referring to eigenvalues of M. So let me zoom in on the top right corner. Uh, yeah, okay, so lambda for R, or mu2, maps to 1 minus lambda 2. Okay. 1 minus lambda 2 to the cross square root of stuff. Okay. Good. So that's mapping the second biggest eigenvalue of the random walk to the second smallest eigenvalue of M. Okay. I still need to somehow get the conductance into the picture. I guess the next step we can just do our favorite inequality, which I feel like we haven't used in a while. So welcome back. Okay. Yeah. So we use just this inequality and hopefully plug it in appropriately. E to the negative conductance squared t over 4 square root of stuff. Okay, so just plugging in. I think it's because of the square root 2 lambda 2. There's a 2 here. Oh, so it should be 2 instead of 4? Yeah, it should be 2 instead of 4. So I guess 4 is still a valid bound. Just, you know. Okay, good. So these are 2's. Okay. Yeah. So you actually use the square root bound, not the other one. Yeah. This is an eigenvalue of R, and this is an eigenvalue of M. Second smallest eigenvalue of M, second largest eigenvalue of. Yeah, I think of like mu as max because it starts as M, and lambda as little because it starts as L. Yeah. I don't know. Okay. Um, good. So okay, this felt like a little bit okay, but okay, fine. All right, here are obviously it was very convenient to assume mu2 was at least a negative mu n, so I can plug it in for gamma. But now, what if mu2 is not bigger? And in particular, how can I kind of force mu n to be away from negative 1? So the answer is going to have the form of changing the random walk. We analyze slightly different but closely related random walk, but one where we can guarantee that mu n is nicely bounded away from negative 1. Right? So the issue is that gamma was, yeah. So if mu n is still negative 1, then, I guess r squared. But then r squared, you'd get another big. Mu 2 will get smaller, but mu n will, like, the bad case is mu n is equal to negative 1. It'll just go to 1, negative 1, 1, negative 1, 1, negative 1. 1's very problematic because now you have two stationary distributions. The graph must be disconnected. That's not good. Yeah. Okay. Yeah. So one way to try to condition is try to sum a bunch of powers of R. Uh, okay, I have something similar in mind. That's a good idea though. So remember when we were doing this prone Frobenius thing, we looked at this alternate walk where I choose some random number of steps first and then take that many steps. So the solution will have this form, but I have something simpler in mind to help, condition the eigenvalues, we sometimes say, make them nicer. So for example, we haven't done this together, but lambda n equals negative 1 actually corresponds to a situation where the graph is bipartite. Mu n is equal to negative 1 happens when the graph is bipartite. Yeah. Add extra edges. Well, that would be, that feels like cheating too much because then you're changing the graph you're walking on a lot. Okay, something like adding self loops. So what we'll call a lazy random walk. So each time I stay with probability 1/2, or 1/2 I take that random step. Okay, so I mean it's like adding self loops, but okay. So the nice thing about this, look at the corresponding random walk matrix. So if I don't know if S is a bad choice, but the random walk matrix is now 1/2 times the identity plus 1/2 times R. Okay, so it's nice and clean. Same eigenvalues, same eigenvectors as R, because I doesn't change anything. Sorry, different eigenvalues, but same eigenvectors. What are the eigenvalues of S? Yeah, the original eigenvalues divided by 2 plus 1/2. So it's raising all the negative ones. Okay. And in particular, everything's actually going to be non-negative. Uh, so uh, now if I sort of have like, I guess I'll write mu2s, mu ns is going to be, something like 1/2 mu2 plus 1/2 1/2 mu n plus 1/2, which is always greater than or equal to 0. Okay. Um, and so in other words, we can just apply the same law from before to this matrix, and then out will come out that thing. And I think this is where the factor of 4 comes from, because you're actually losing a factor of 2 here when you plug it in. And when I copy pasted, yeah, I made a mistake. Yeah. Yeah. Yeah, what does it mean? I guess it's always a little bit. Mm, yeah, yeah, yeah. Well, yeah, I think the question was just in general positive vectors going in. So I think so in general eigenvectors aren't necessarily interpretable. There's only some special cases where the first one corresponded to stationary distribution and things like this. That's the exception and not the rule. And R is really, this composition of n different eigenvectors, all of which act on your vector x. And the sum of them, what comes out is pretty reasonable because the sum will give you the original random walk and then that'll give you the thing. A singular particular eigenvector, except for a couple cases we can peel out and interpret, I think don't necessarily have obvious meaning. Yeah. So there's just like weird things you can work out. Oh, if the smallest eigenvalue is -1, then it has to be bipartite, and as an exercise, you can prove the if and only if. Things like this. So there's some connections, some properties, but not all connections and all properties. So it's a miracle that we can get anything out of these matrices is maybe one way to look at it. Yeah. Okay. Good. So the stationary distribution, which is just taking one half, only stepping with probability one half in each step, will converge pretty fast to the stationary distribution of the random walk, which is the same. I mean, the stationary distribution doesn't change when you do a lazy random walk. Okay, because all the eigenvectors are the same. Good. Um, okay, so that motivates conductance a little bit, right? So this bound, it's really saying that lambda two. Yeah, sorry. Yeah. Yeah. So for example, a bipartite graph, right, depending on your starting point, will never converge to a stationary distribution. So we'll never be able to prove a statement of this form for the original matrix R, because it'll never converge. Just go back and forth, back and forth, back and forth. I don't know if that's true always, or if it is true, one needs to show it could be true, but you'd have to work it out. Yeah, but there's a certain worst case sense in which S is more convenient. Okay, so the moral of this story is that there's a strong connection between conductance and mixing time, which is a little bit intuitive too, because a graph with very low conductance, like two large clicks, connected by just a single edge, a random walk is just going to get stuck in the click and never be able to get out. But the stationary distribution is basically going to be uniform over everything. So uh, yeah, so it's good to see like it's we want to take like graph understanding and map it out to these random walks, and these connections are hard to make in general. But luckily we can. Okay, but we'll need to prove Cheeger's inequality. So Cheeger's inequality says that conductance is closely related to the second eigenvalue of M, second smallest. The first inequality is not so hard to show and left as an exercise. And the second inequality, um, uh, the same dustbin as the multiplicative turnoff bound. And but the second inequality is much not nearly so straightforward and very nice and also algorithmic. Okay, so what we're actually going to do is we're going to do an algorithm that will compute lambda 2 and the second eigenvector and output a cut with conductance at most square root 2 lambda 2. Okay, so we're not just doing a mathematical bound, we're going to get an algorithm. All right. So good. Good. Okay. So high level ideas. Apparently there aren't any. Let's see what's here. Um, okay. So, all right. The matrix M we know has this form. Uh, if I'm listing the eigenvalues in increasing order, lambda 1 is 0. And I have all these, this orthonormal basis. V1 should be, yeah, one sec. What else is there? Okay. So V1 is the eigenvector for eigenvalue 1 of R. That's something proportional to square root D, if you remember. Um, and so lambda 2, which is equal to V2 and V2. Okay, and what else is there? So that can also be seen as minimizing y subject to y square root d is equal to 0. Right? So if you kind of pull out the smallest eigenvectors, the eigenvector's smallest eigenvalue, right? And then if you think about our proof, then we kind of induct on the orthogonal subspace to get the remaining eigenvectors. So the minimum orthogonal is always going to give you M2. Okay. And I think there's a little bit more intuition here. Yeah. If I plug in, okay, so let me explain this a little bit. So M was equal to, if I remember correctly, D minus 1/2 L D minus 1/2. Okay. So if we set X to be D minus 1/2 Y, okay, which means that Y is equal to D to the 1/2 X, and start plugging things in, then y is really y d to the minus 1/2 L d to the minus 1/2 Y. And so that becomes xlx. Y is d to the 1/2 X, that becomes x dx. Okay? And then subject to xd is equal to 0 is the same as y squared root d. Okay? Now, okay, the reason why this starts to become interesting is that think about x as the indicator vector for a set S. So let's say X is, I have a set S with volume less than half, so a smaller set. And I'll put a 1 for all those vertices and 0 everywhere else. Okay. So this will compute the weight of the cut of S. Remember, because XLX is going to do endpoint minus endpoint squared for all the edges. So for S, I have 1. For everything else, I have 0. So if an edge is on the S side, it's just 0 squared. If edge is on the other side, that's 0 squared. But if you have an edge across the cut, you'll get 1. 1 minus 0 squared. Right? So the numerator is going to give you the weight of the cut. The denominator is going to be summing up the degrees. So for all the vertices in S, you're going to get a 1 times the degree. Okay? So this is actually relaxing to some extent the volume, the conductance. There's a little issue here. The sum of degrees needs to be 0. Okay, but that's okay. Yeah. Yeah. So for a single edge, E is equal to UV. This was the outer product of having this is like the indicator vector of just one vertex. So XLE, X for any X, is going to be, taking the dot product with each of these terms times XU minus XV. And then LE is just the sum of these terms. I mean, L is the sum of these for every edge times the weight. So it's just taking, X is some kind of potentials on the vertices, and it's just for every edge looking at the difference of the endpoints squared. Okay? If it's a weighted graph, it'll be a weighted sum of these LEs. Yes, yes. So I'm looking at a particular x that puts value 1 on every vertex in S and 0 on all the other values. Yeah, so the edges inside S, they just become 1 minus 1 squared. The edges outside S become 0 minus 0 squared. The edges in the cut become 1 minus 0 squared. And they only add up. And into the, yeah. So it would be a weighted sum of LE. So it would be 10 times this LE plus 20 times the next one. Yeah. Okay, so uh, now what we want to do is we want to go in the opposite direction. So there's this sort of superficial, I mean, at the moment, somewhat superficial connection between lambda 2 and a term that looks a little bit like conductance in the sense that I could plug in the indicator vector of a set and out comes the conductance from this ratio. It's not necessarily orthogonal to D though, so that's a different issue. And but what we want to do is we want to take the vector x that solves this optimization problem. So x will be orthogonal to the degrees, and it will minimize this ratio. It corresponds to the second eigenvector of y, but it's slightly different. And I want to output some set. Where the conductance is good. So, okay, any idea how? So I give you this vector x, right? It's assigning values to all the vertices. I want to output a cut. Yeah. Oh, yeah. Yeah, so actually this is an algorithm you've seen before. We're just going to line up the vertices in increasing order of value, and then we'll look for the best cut. Okay, so it's another sweep cut, correlated rounding kind of thing. Okay, it's a little different because, for example, like x doesn't sum to 1 or something, so some things are going to get weird. You should expect things to get weird because we're going to get some square root instead of just lambda 2. So we'll have to make some adjustments. Okay, I think intuitively part of what's going on is that eigenvalues, eigenvectors are really living in L2 space, right? You're minimizing sum of squares types terms, right? And we're trying to do something that cuts are really in L1 space, like cut metrics or L1 metrics, right? So you the square root is kind of going from this crisscross of geometries. Yeah. Well, I mean, I'm saying, like cuts are like really. I'm speaking kind of informally, but sort of belong to L1 space in the sense that all our cut problems, if you had a solution, an L1 relaxation of sparsest cut or max flow, things like this, we could always round it without any loss. There's a strong connection between cuts and L1 metrics. Um, but this oracle, a second eigenvalue, feels like it's really living in Euclidean L2 space, right? Because it's minimizing these quadratics, yeah. Yeah, kind of, morally, yeah. Uh, but maybe keep an eye out for where we sort of address, jumping this gap from eigenvectors and eigenvalues, which seem to properly be associated with L2, into the land of cuts and stuff, which seem to be properly associated with L1. Okay, so that's right. So we'll do this same algorithm. Uh, yeah. Okay, so that's our goal now. We're going to show that the line embedding is useful. Okay? And somewhere we're gonna have to do something weird because square root shows up, and that's when I'll ask for your help. Okay. All right. So I meant to hide more of this originally. Okay, that's okay. Uh, ignore proof. Let's start with lemma. So I'm going to do something a little bit uh, easier first. Okay. I'm going to say, suppose X had non-negative entries. That's in general not going to be true for us because actually X needs dot product D needs to be 0. So that cannot possibly be true. Um, but suppose X was non-negative, then the claim is that XLX is at least phi squared over 2 x dx. Okay. So phi is the conductance of the whole graph. Yeah. Okay. So let's say S is supported by K vertices. Okay. Which I'll write V1 to Vk in decreasing order with respect to the value in X. Yeah, non-zero entries, which for us is strictly positive because they're non-negative to begin with. And I'll let SI always denote the 10 biggest entries, 11 biggest entries, things like this. So the first part of the proof, we're just going to expand out this term. Um, okay, so this volume-like term. So this is all it is, right? So x dx is just summing over all the vertices that are non-zero value, their x value times the degree of the vertex. Okay, nothing special. Um, this step is kind of neat. Uh, so the degree is the same as the difference in volume between top 10 vertices minus top 9 vertices, right? The only difference is the degree of the 10th vertex. And then we'll interchange sums. Okay, so I've interchanged sums, okay, between volume and x squared. Okay. Or is there a change from term? Yeah, I feel like, how do you describe this? Uh, so volume SI is going to be next to x squared VI, and then from the VI plus 1 term, it's going to appear here with a negative sign. So that's why you get x squared VI minus x squared VI plus 1. Okay, and note that V sub k plus 1 is 0 because it's not in the support. So yeah, we don't have to add in an extra term or anything like that. Yeah, let's look at volume, just volume of some set SI. So this is multiplied against x squared VI. So that's this term. But if you went to I plus 1, then SI would appear as SI plus 1 minus 1 in the next term in the sum. And that will get you a negative x squared VI plus 1. So volume of SI is ultimately multiplied against x squared VI and negative x squared VI plus 1 over the course of this sum. Yeah, it's interchanging something. And I don't know, it looks like the same index. Uh, rearranged in some way. Okay. All right, here is now where you jump in. Okay, what do we do next? Not yet, actually. So what do I know about phi times volume SI? It's at least the value of the cut because of conductance. Okay, so I also forgot to mention that the volume of our support is assumed to be small, at most half of the volume of the entire graph. That's important because conductance always looks at the smaller side, you know. Here I'm just calling a set as small if the volume is at most half. So, okay, good. So this is at least the sum from 1 to k, the weight of the cut SI, x squared VI minus x squared VI plus 1. Okay. Sorry? Yeah, so now we're just plugging in the definition of conductance. Okay. And now here's something pretty cool. So this is a this is a bunch of edges, right? And not only that, but remember we're listing the vertices in increasing order. Um, in decreasing order. Let me make sure I do this correctly. Yeah. Okay. So you can sum over all the edges in the graph, UV, the absolute value of x squared u minus x squared v times the weight of the edge. Okay. So if the edge appeared, say in this cut in this term, remember the x's are in decreasing order. So this is the same as the absolute difference of the endpoints. Okay, because this is always bigger than that one, the way we've listed things. Okay, cool. And now what's the next step? Yeah. Well, no, because I've listed them in decreasing order. You look at the top right here. xv1 greater than or equal to xv2. Yeah. Okay. Good. Oh, should I have been a less than equal to? Should have been less than equal to. Do you feel okay with this? Right. Conductance is the minimum, right? So phi times volume is a lower bound than the weight of any cut. That's over a small set. Okay. Okay. Well, okay, so maybe I should remind you that the goal is eventually for this thing to be, it's actually equal. So for every edge in the graph, it could be less than equal to because it's over all edges. So for every edge in the graph, it appears either in one of these terms because it involves one of these vertices, or both endpoints have value 0 anyway. That's why they were left out because we're summing over all the vertices with non-zero value. Yeah. But less than equals all we needed, so that would also be okay. Okay, so now the issue is how do I deal with this? Well, maybe it would be helpful if I wrote it out like uh, absolute value, WE. Okay, so all the x's are non-negative, and this should be an absolute value, not a parentheses. Okay, so at some level I need to somehow deal with this. I am trying to get, eventually bring XLX into the picture. Yeah, so number XLX is equal to the sum over all edges equals UV, the weight of the edge, XU minus XV squared. Which almost looks like something we have, right? We have weight E, and we have absolute value of XU minus XV. But I really wanted something like XU minus XV squared. Okay, maybe what I can do, I'll write what I claim it is, and you can tell me why. XLX times the sum over all edges, E is equal to UV, uh, weight of E, XU plus XV squared, all of this square root. Why? I don't know if we've used this inequality before, but it's a super duper useful one. It's exactly Cauchy-Schwarz. Okay, so Cauchy-Schwarz says the sum of AB is less than or equal to the square root of sum of A squared, sum of B squared. I mean, it's AI and BI. Okay, so I do XU minus XV times square root of WE. That's A. And then XU plus XV times square root of WE is B. So the square root, this you'll get this term. And then what's left is square root of WE squared times XU plus XV squared. Yeah, so you split up the WE into two square roots when you play Cauchy-Schwarz. Now I want to make this look like x dx. So to that end, rats. All right, sum E equals UV. Well, let me put it this way. All right, XU plus XV squared is at most 2 XU XV. Why? I don't know if that's technically AF. Well, there's a factor of 2, right? So, right? Um, and meanwhile, 0 is at most a minus b squared, which is equal to a squared minus 2ab plus b squared. So that means 2ab is always less than or equal to a squared plus b squared. Oh, good point. Did I create some problems? Uh, did I make something up again? Oh, no, no. So this is okay, right? So this is less than or equal to 2a squared plus b squared. Oh, okay. So what I wanted was, this is not what I wanted. Okay. I'm kind of bummed out because we won't finish today. and I don't know what will happen on Monday, like cosmologically speaking. Okay, so if we plug this in, then this term here is can be written as a sum over all vertices, 2 times so over all let me do it slowly. Summing over all edges, E equals UV, the weight of the edge times 2xu squared plus 2x squared V. This one? This one? This is equal. And then if you look at this implies that 2ab is at most a squared b squared. So there's a 2 here that I didn't write. Yeah. Okay. All right. Got a little messy and I lost my confidence, but we're okay. This is okay. Right? So this term up here in red, summing over all, for every vertex, it's seeing its edge twice and summing x squared u. Right? So that'll give you 2x dx, or yeah, 2x dx. Okay. So I'm running out of space. This is at most xlx times 2 times x dx. Okay? And and then you rearrange and you get the thing you wanted. Okay? So the square root entered, to be clear, when we applied Cauchy-Schwarz. Okay? So Cauchy-Schwarz is a pain. That's why we don't have a strong enough bound, but it's the best we're going to get. Yeah, good. Okay. All right. So, what's the point? Okay. All right. So, okay. So what should we do? So, we're 5 minutes over. We only have a couple lemmas left. And I don't know if it'll be like super fun to do this again on Wednesday and do 10 minutes warm up and stuff. So one is, you can go off and read the last 2 lemmas. The remaining 2 lemmas are much easier. In fact, this one I think I just have hidden the boxes. So we can do that. I can also keep going and finish it because there's no class coming next. But I can let anyone leave if they want to leave, and then the recording will still get posted to YouTube. So basically, I just don't do it at all, and it's on you to go off and read the last 2 lemmas, or I'll let anyone who wants to leave, and then I'll just finish it. Okay, I'm just gonna keep go. Okay, so I'm gonna keep going, but please don't be shy to leave, and I'll still post it on YouTube. Plus, everything's in the notes, so you won't be missing too much. Okay, I'll be missing a staff meeting, but there's no loss there. Um, huh? Did I do this on purpose? Okay, so okay, so I want to get to this space where I can focus on x being non-negative. Okay, and so I'm going to need 2 steps to get there. Well, let me first overview the 2 lemmas. One lemma is that if I take my vector x and I split it into the positive part and the negative part, So x plus just has all the positive entries in x, and everything else is 0. X minus has a negative entries in x, everything else is negative. Then, uh, if I split up xlx into the two, it'll just go down in value. And if I split up x dx into the two values, it only goes up in value. So that means if you start combining these things, that means that x plus lx plus x minus lx minus over the things for the d's. Okay, this should only be smaller. Okay, which means that one of the two must have better ratio. Either the plus is better or the minus one is better. So if you have a over b, or if you have, yeah, so you have two ratios, a over b and c over d. The smaller of the two ratios is always smaller than a plus c over b plus d, which you can just work out and double check. Okay, so I have kind of, x plus and x minus are both candidates for the, what we just did, because all the entries are non-negative, and one of the two will have good ratio. Okay, but one remaining issue is that we required the support of our non-negative vector to be small, like in total volume, right? So maybe you split it up, your original vector x, into x plus and x minus, and you realize, oh, x plus has a good ratio, x minus doesn't, okay? But the problem is that x plus, the support, that full set S is too big. The total volume is bigger than the volume, half the volume of the graph. So remember that one step in the earlier proof where we used the conductance bound? That only applies to small sets. So we wouldn't be able to take that step and apply it to x plus. So what the other lemma is going to do is it says that, okay, I can always take x and I can shift it. I can add alpha to every entry, okay? And the ratio will only go down. So if x is already orthogonal to the degree, and then I do a uniform shift, either down or up, but every coordinate changes by the same amount, it's only going to help this ratio. Okay, so those are our two lemmas we need to prove, and we're done. Why? So you take x, right, and you want to do this x plus x minus, but it's not balanced. So you take x and you increase or decrease all of the coordinates until half of them by volume have positive coordinate, and half of them by volume have negative coordinate. Then when you split it up into x plus x minus, the support of each side has at most half the graph in its volume. And then you can apply our previous lemma. Okay, so those are our two lemmas. You can always do a alpha, this shift by alpha, and you can split it up into x plus x minus. It does not matter. Alpha could be any real number. So you can shift them up or you can shift them down. It just has to be uniform. Okay, so, okay, which one do you want to do first? First lemma or second lemma? Okay. No, I'm not sure what the or reason is actually. Let me erase this. Because I'm like looking at it now, I'm like, oh, should I have done it the other way? Um, sorry. The reason I have to do this is because I think it's hiding a big white square, so I can't just use the eraser. Okay. So, all right, so let's start the proof. Okay. So let's look at this lemma. The claim is that if I start with x orthogonal to the degrees, and I shift it uniformly, it's only going to help the ratio. So, Okay. The first claim is that YLY is equal to XLX. Why is that? Well, okay, so Y will no longer be orthogonal to D because you're adding the all ones vector, and all ones vector times D is not zero. So XD is equal to zero, but as soon as you start adding, so it won't be orthogonal. But the claim is only focused on the numerator. The claim is that for the Laplacian, if I look at XLX and I increase all the coordinates uniformly or decrease uniformly, the value of XLX doesn't change. Yeah. Yeah, so XLX is always this XU minus XV squared, right? So if I increase both coordinates by one, XU minus XV squared hasn't changed. So L has always been, the all ones vector has always been orthogonal to L. It's also the eigenvector corresponding to eigenvalue 1, 0. So, okay, so that doesn't change. So all that's left is to consider the denominator. So here's this claim. Okay, so you can start with y dy. You write it out x plus alpha 1s d x plus alpha 1s. And the claim is, so there's the xx squared, or there should be x dx. And then there's an alpha squared d1s. Right. Alpha squared 1s comma d1s would be just the sum of degrees. So at each, there's an x dx. So let me fix that. Okay. But the cross term dropped, right? Why? Why did that middle term drop? That middle term should look like 2 times alpha 1s comma dx. Okay, good. So 1's dx is equal to dx, which is equal to 0. Okay. So, right, so as you move alpha in any plus or minus, the numerator does not change, but the denominator increases. So yeah, uh, this was initially, it should have been 1's d1s, and then the diagonal matrix of degree applied to the all ones vector will give you 1d. Yeah. Okay, so that's one lemma. The other lemma, oh, maybe I put it last because it's trickier. Is it trickier? Okay, so, okay. So, okay, let's do the red one first. Red one's the trickier one. Um, okay, so I have this XLX term, okay, and I want to split into positive, negative. So let me just write that out uh, like this, okay. And so you'll get, I thought I wrote this. Okay, good. Okay, so, uh, you know, a minus b squared is a squared plus b squared minus 2ab, right? So the x plus is over here from the first difference, the x minus term from the second difference. And so we have these cross terms left. This is the 2ab, right? Okay, so we just need to figure out what to do with this thing. Okay, so the claim, okay, so in other words, we have a claim of this form, right? We have, so what I want to show, I want to show that this thing is less than equal to 0. Because if that is less than equal to 0, then this negated term is positive, so you can just drop it. So why is this true for any AB? Sure. hmm Okay, that actually also works. Okay, good. So um, here's one argument. So only one of A and A minus is non-zero. So A plus times A minus is always 0. B plus times B minus is always 0. So you're left with these cross terms, negative B plus times A minus and negative B minus times A plus. But all those values are the A minuses and B pluses, they're all non-negative. They have negative signs in front. So the whole thing will be less than or equal to 0. Yeah, that's probably better than what I had. Mine was like, oh, if A is bigger than B, uh, then this is positive and this is negative. I mean, greater than or equals 0, less than or equals 0, if A is bigger than B. And if A is not bigger than B, you just reverse the rows of A and B. Yeah, but in particular, you start with A and B, and A plus is the positive part of A, and A minus is the negative part of A. A plus is 5, A minus is 0. Yeah. Well, here this is just a number. Yeah. Okay. So that's why that inequality is okay. And I guess there's this one. Do you guys want to do this one? This one's not so bad. Uh, so x dx is equal to x plus dx plus x minus dx minus plus, I guess, the cross terms, x plus dx minus plus, oh, is it just that times 2? Okay. And then, oh, I got it wrong. There's a minus sign. Good. Otherwise, we would have been in trouble. Okay. So all the entries of x are, I guess this is actually equal to 0 because of the complementarity. But if you're even lazier, then positive numbers, d. But if you look more closely, whenever a coordinate is positive, the other one is 0. So this actually, and this is a diagonal matrix, so it comes out to 0. Okay, so that is all the lemmas. Yeah, yeah. Okay, good, good. So, all right, so that's basically the claim. If you want to actually, the actual algorithm scans and pulls out the best set, S, okay? And the only adjustment you would make here, okay, so what we've now done is we've at least proven the Cheeger's bound. Okay, we related lambda 2 to x dx. So to remind us, you start with x, you shift everything so it's evenly balanced between the coordinates with negative value and positive value. And then you do the x plus x minus split. And then whichever side has a better ratio, you apply this proof. And you'll show that, x plus lx plus is greater than or equal to this thing, x plus dx times conductance, and then you can replace x plus with the original x because x plus is only better. So that proves Cheeger's bound. If you want to actually get the set, the algorithm, okay, then what you do is you replace this bound with alpha, where alpha is equal to the min conductance over the sets that we consider in our algorithm, S1 to Sk. Okay, and then all of these become alphas. And here you're only looking at the sets Si, so this part is still okay. And then, and then that'll show it's ultimately okay. Okay, so you can also pull out the line sweep from this, but I've gone way over, so we'll call it a day. Enjoy the solar eclipse. If the world comes to an end, I hope you enjoyed your last lecture in this class. Okay, I'll see you guys Wednesday. Office hours will be on Wednesday.